Good evening, sir. We'll start the meeting in 5 minutes.
Hi. Shall we just try whether the sharing works? Am I audible?
Yes, sir. Yes, sir. You're audible.
Okay. Shall we just try whether the sharing is working okay? Shall I just try sharing the screen?
Yes, sir. Yes, sir. You can try.
Is the screen visible?
Yes, sir. It's visible.
Okay, let me just try. Oh. Unfortunately, it doesn't let me scroll down page by page. Let me just check that. Now, maybe this is better. Okay, so I can share the screen whenever we are starting.
Good evening, everyone. We will now pause for a brief yet enlightening webinar. It is my honor to invite Dr. Arulmozhi, coordinator of the Astronomy and Innovative Forum, to deliver a warm welcome address, followed by Ms. Evasha from First Wiki, who will introduce our esteemed speaker for the webinar.
Good evening, everyone. It's with a great pleasure and honor that I welcome you all on behalf of the Loyola College Management, Department of Physics, and the Loyola Astronomy and Innovative Forum to this exciting and insightful webinar series. I would like to extend a heartfelt welcome to each one of you, and we are grateful to have such active participants with us today. So I'm especially delighted to welcome our esteemed speaker, Dr. Arun. His deep expertise and passion for astroparticle physics and quantum field theory are well reflected in his numerous impactful publications. We are incredibly fortunate to have him with us today, and I'm confident that his talk will offer valuable insights and stimulate thought provoking discussions. So, Dr. Arun is truly the perfect person to lead us through this fascinating subject, and we look forward to benefiting from his wealth of knowledge. So, in addition to So it's a great pleasure and honor that I welcome you all on behalf of the Loyola College Management, Physics Department, and the Loyola Innovative and Astronomy Forum to this exciting and insightful webinar series. So I would like to extend a warm welcome to each one of you, and we are very grateful to have such an active participants on this day. So I'm especially delighted to welcome our esteemed speaker, Dr. Arun, His deep expertise and passion for astroparticle physics and quantum field theory are well reflected in his numerous impactful publications. So we are incredibly fortunate to have him with us today. So I welcome you, sir. I am confident that his talk will offer valuable insights and stimulate thought-provoking discussions. So Dr. Arun is truly the perfect person to lead us through this fascinating subject, and we look forward to benefiting from his wealth of knowledge. So, in addition of welcoming you all, I would also like to extend my gratitude to the forum in charges and members who have worked tirelessly to bring this event to life. So, your dedication and commitment to fostering an environment of learning and innovation are truly commendable. So, once again, I welcome you, everyone, welcome you all. So let's make the most of this opportunity to learn, share, and grow together. So thank you. I hope you all enjoy this session. So welcome, sir. We welcome you all.
Good evening, everybody. It's a great honor for me to introduce the speaker of the day, Dr. Arun Talaplil. So, Dr. Arun M. Talaplil is currently an associate professor and the Dean of Science in the Department of Physics at the Indian Institute of Science, Education and Research, Pune. He holds a PhD and MS in Physics from the University of Chicago and a BE in Electrical Engineering along with an MSc in Physics from the Birla Institute of Technology and Science, Pilani. His academic journey includes prestigious fellowships such as the Subramanian Chandrasekhar Memorial Fellowship and the Sydney Blumenthal Fellowship, with postdoctoral experience at Rutgers University's NHETC and a rich portfolio of contributions to particle physics. Dr. Talaplil's work is published extensively in renowned scientific journals. His research spans theoretical physics, including significant work on the Higgs boson, neutrino interactions, and collider physics. He has also been an active member in academic committees, organized conferences, and has a passion for teaching, having received nominations for teaching excellence during his time at the University of Chicago. It is a great honor to listen to such a personality today. Without further ado, I now invite the speaker to take over the session.
So it's just to make sure, am I audible to all of you? Just making sure I'm audible. Am I audible?
Yes, sir.
Okay.
Yes, sir.
So it's truly a pleasure to be here, and I look forward to interacting with all of you during the talk as well as after the talk. So let me just try sharing the screen. And while I do that, so I want to thank the Loyola College as well as the Department of Physics organizers, faculty, everyone for giving me this opportunity to talk to you all. So let me just try sharing the screen. Hopefully is the screen visible to everyone?
Yes, sir.
Okay. Okay. So the screen is still visible, right? Just checking one last time before I start. Sorry, am I audible? Hello. Is there an audio issue? Sorry,
Yes, sir. Yes, sir.
Yeah.
You are audible.
Okay. So it's a bit of a black box. So just kindly just let me know if the screen is not visible or something. Huh? So I have titled the talk as of Stardust Memories. So there is a reason behind it, because one of the themes I want to convey to you is that in some sense we are all remnants of stars which have long since passed away. All the heavy elements, all the elements in our bodies, elements which make Earth, predominantly were all cooked up in some heart of a star or in some process involving stars. So I have intended this talk more as a informal interaction, informal and semi-pedagogical thing. So I want to encourage all of you to ask questions even in between the talk. In case somebody is writing the chat, and since in my full screen mode, I will not be able to look at the chat, I'm not able to see the chat, I'll request one of the organizers to read it out. And if it's a quick question, I'll be more than happy to answer it. If it is something which requires a longer conversation, I will, request that we talk about it after the talk. But I would like all of you to interact. I've meant it as a interactive, informal talk, semi-pedagogical. Now, second. Some small issue. Let me just try to fix it. Okay, so this idea of that we are made of star stuff is actually taken from a very old quote by Carl Sagan. So Carl Sagan in one of his interviews said, in some sense the cosmos is within all of us, because as I said, his idea was that, or what he was trying to imply is that all the heavy elements which we are made of were in one way or the other cooked up in stars. Okay? So either they were produced in a supernova explosion, like a supernova is a process where some incredibly massive star basically explodes, and the center of this you're left with a neutron star, and during this very energetic supernova explosion, some of these heavy elements are made. Elements up to iron can actually be made in the nuclear fusion processes inside conventional stars. But beyond iron, you cannot cook them inside stars. So either you need things like a supernova or things like a neutron star merger. Just to ask, is my cursor visible when I'm pointing at something on the screen? Is the cursor visible to all of you?
Yes, sir.
Okay, perfect. So I'll use a cursor sometimes as a proxy to point at things. Okay, so there are conventional stars, as all of you know, like the sun is one. Then if you look up in the night sky, you see various stars. Today, I want to focus on one particular class of stars, which are broadly called astrophysical compact objects. They include objects like a white dwarf, neutron star, black hole. Some of these names you might have heard and you will be familiar with. So I want to tell you a little bit about how some of these astrophysical objects, compact astrophysical objects, can actually be leveraged to understand about physics, which is otherwise inaccessible in terrestrial experiments. Moreover, some of these astrophysical objects can actually be used as experimental labs to look for new physical phenomena. Okay, so before telling you these, I want to give you a flavor, a semi-quantitative flavor of what these objects are. Okay, and talking to your organizers and Dr. Arulmozhi today, I understand that many of you are physics majors. So I'll keep pitching at the level of a junior physics major, and if there is anything which is unclear, please stop and ask. Okay, please do not hesitate to stop and ask, what does this mean? How did you get this expression? Because like I said, I am intending it as an informal thing where hopefully I can convey to you something useful and interesting. And I also get to know that there is a sky watching session later today. So, I think it's a nice segue to your sky watching session. Okay, so the first thing I want to kind of remind you is something called the equation of hydrostatic equilibrium. Okay, so to do that, imagine that there is a star, like a white dwarf or a neutron star. Okay, imagine two virtual, shells inside it. Okay, now if one were to ask, okay, I draw a Gaussian cylinder here. Now, just from the Newton's law of gravitation and equilibrium, you could say that the force acting on the cylinder is minus gm by r square, where m of r is the mass inside this radius r, okay, times the mass of the cylinder, which is given by, let's say, density times area times dr, where dr is the size of the cylinder. Okay, now you take the area to the other side, and you get dp by dr is equal to minus gm rho by r square, where p is the pressure. So this is usually called the equation of hydrostatic equilibrium. So as long as the curvature of space-time is not too significant, this is an equation you can use to understand, at least crudely, some of the aspects of equilibrium in a star. If space-time curvature is important, you have to generalize this. This is sometimes called the Tolman-Oppenheimer-Volkoff equation, TOV equation. Okay, but for our purposes, we'll work with this equation of hydrostatic equilibrium. Another ingredient which I want to remind you or tell you if you are not familiar with is, see, in quantum mechanics, you cannot have any momenta you want, because there is an intrinsic uncertainty involved from the Heisenberg uncertainty principle. So the momenta, in some sense, is if you have a box of size L or one-dimensional line of size L, the momenta is uncertain up to a factor h by L, where h is the Planck's constant. Okay, so if you're looking in 3-dimension, okay, 3-dimensional momentum space, in some senses, momentum space is divided into discrete cells, each of size or volume h by L cube, because there's h by L in the kx direction, h by L in the ky direction, h by L in the kz direction. Okay, so unlike classical mechanics or classical statistical mechanics, one of the ingredients which quantum statistical mechanics tells you is that the momentum space, there should be some discretization coming from this. Okay, are we all on the same page? Please ask if something is unknown to you or you have not seen this before. Okay. Okay, so if we were to think of momentum space, okay, at 0 temperature, and let's say, the states are filled up to some momenta level, usually called the Fermi momenta, which is denoted by Kf here. Okay. You could ask, how many fermions can you accommodate inside this Fermi sphere? Yeah. Remembering that there are unit cells of volume h by L whole cube, okay, because momenta. So it's very easy. So the total volume of the sphere for Kf large is 4 by 3 pi Kf cube. Okay. How many cells are there inside this 4 by 3 pi Kf cube? You divide it by the volume of each cell, which is h cube by V. That is this h by L whole cube. Okay. Now, since these are fermions, and you know that you can't put fermions with exactly same quantum numbers on top of each other, okay, but you can have, let's say, if it's an electron specifically, you could have like spin up and spin down, for example, and that is this factor. So the question is, what is the number of particles which can be accommodated inside this Fermi sphere? It's given by this equation 3. Okay, 4 by 3 pi Kf cube divided by h cube by V, and you multiply by a factor of 2 for the spin. So from this, we directly see that the Fermi momenta, the Kf, the Fermi momenta is the maximum momenta in this filled thing, that is what is denoted by Kf, goes like number density to the power 1 by 3. Okay. Now, maybe I should have said this a few minutes back. Why are we talking about all this? See, one of the reasons is that unlike conventional stars, these astrophysical compact objects, which consist of white dwarfs, neutron stars, etc., quintessentially depend on some quantum properties, specifically things like Fermi-Dirac statistics or Pauli-degeneracy pressure for their stability. Okay, so in conventional stars, things like radiation pressure, etc., balance the gravitational pull. But things like white dwarfs, neutron stars are in some sense quantum stars. Their stability is predicated on things which are much more quintessentially quantum. Things like degeneracy pressure or equivalently Fermi-Dirac statistics. So I'm trying to give you a flavor of what some characteristics of these objects are, and then tell you, what we can do with them. Okay. So Kf, in the case of fermions, a Fermi gas, goes like number density to the power 1 by 3. Now, if you want to know what the Fermi energy is, okay, in the non-relativistic case, in the non-relativistic case, the energy is given by momenta square by 2m. So that's Kf square by 2m. So you take this Kf, you square it. So the Fermi energy goes like number density to the power 2 by 3. Okay, but notice that all the Fermi momenta is independent of the mass of the constituent particle. The Fermi energy has a mass dependence because there's an m in the denominator. Okay, but the main point is that Fermi energy goes like n to the power 2 by 3. The Fermi momenta goes like n to the power 1 by 3, and this 1 by 3 is a consequence of the fact that this momenta space is discrete because of the Heisenberg uncertainty principle. Now, probably from your basic courses in thermodynamics, statistical mechanics, you might recollect that for a non-relativistic set of particles, the pressure is given by 2/3 the energy density. Okay. So what is energy density here? So what is the total energy? It's number of particles n times some energy, which is like some fraction of energy. Okay. So I should say, see, I'm doing a lot of order 1 estimates. Okay. So order 1 factors, etc., factors of pi, etc., I'm not being careful about because I want to give you a flavor of some important salient points. Okay, for stars, and then compare it to certain other more exotic objects we will see later. Okay, so the total energy order of magnitude goes like total number of particles times EF. EF was Fermi energy, and since it's an energy density, U int is energy density, you divide it by volume. Okay, and EF goes like n to the power 2 by 3, so there is an extra n by v, so it's n times n to the power 2 by 3. So for a non-relativistic Fermi gas, the pressure, because of Fermi-Dirac statistics, see, because the fact that you have an EF and EF is not 0 is because you could not put all the particles here near the origin, because you can't pack more than 2 electrons with opposite spins at one point. You have to, kind of stack them up, and that's what's giving you the non-zero EF. That's what gives you a sphere rather than a small point or something concentrated to the origin. So the fact that there is a finite EF is a consequence of Fermi-Dirac statistics or Pauli degeneracy pressure. Okay, so for a non-relativistic Fermi gas, the pressure goes like number density to the power 5 by 3, or if you divide and multiply by mass, etc., it goes like density to the power 4 by 3. Okay, I'll just pause here for like 2 seconds and just to take any questions or if there's something which was unclear. Please feel free to ask. Okay, don't be inhibited. There are no stupid questions ever. Okay, just making sure there is silence because there are no questions and not because I'm disconnected. Can one of the organizers just tell me I'm still connected? Hello, am I connected?
Sir, no questions has been posted yet, sir. We will
Yeah,
let you know if there are any
I
questions.
yeah. I'll just request the organizers, sometimes since I can't see the interface, just to acknowledge me when because it's sometimes unclear to me whether I've lost connection because of bandwidth. So I'll just request one of the organizers to acknowledge. Otherwise, I'll be confused whether it's because there are no questions or whether it's disconnected. Thank you. Okay, so now with this equation 7, okay, so giving pressure as a function of density, this is called the equation of state. You can use equation 7 and equation 2. Okay, see, there is pressure on the left hand side, there's density on the right hand side. There is an equation 7 which tells you how pressure and density are related. If you do this carefully, you will get what are the factors sitting in front, etc., which I have not done. So you can solve these two, okay, basically, and prove that in the non-relativistic degeneracy case with fermion gas, the radius goes like 1 by cube root of m. Is there a question? Okay, maybe the mic was accidentally on. Okay, so the point is, just to summarize, you take equation 7, that's an equation of state for a non-relativistic degenerate Fermi gas. You use that equation of hydrostatic equilibrium, you solve it, and you can show, and it's easy to do, especially these days. Back in the day, it was not easy to do. This was a calculation first done by Chandrasekhar in 1930. You can show that the radius of the star, okay, will be proportional to 1 by cube root of it. So as the mass increases, the radius decreases. Okay, and in 1930, there were only a few white dwarfs known, or what we call as white dwarfs. Okay, so one of the candidates which was known even at that time is actually what we now call Sirius B. Okay, so Sirius is, you might have heard it is like the brightest star in the sky. It's actually, part of this constellation called Canis Major. Canis Major is like this dog which is following the hunter. The hunter is Orion. So Sirius is, I think it's the eye of the dog or something. But it's actually not a single star. It's actually two stars, except one of the stars is extremely bright. The Sirius A is extremely bright, but there is actually a companion to this, which is actually a white dwarf. So that is what is shown here in the lower left corner of the screen. You see that small white dwarf dot in the lower left corner? That's actually a white dwarf star. Okay, and astronomers had estimated what its mass and size should be, and from this relation, okay, so this R going like m to the power minus 1 by 3. If you take, okay, the Sirius B roughly had a mass of a solar mass. The prediction was that it's around 10 to the power 4 kilometers in radius, and which very nicely matched the observation at that time. Okay, so this was a story in 1930. But Chandrasekhar was little worried, and I'll tell you before that I should maybe just flash a few other pictures. So for example, this is a ring nebula. It's in the constellation Lyra. Okay, so some gigantic star has exploded or ejected its envelope, and you can see at the center this white dot. Right? That's actually another white dwarf. Okay, so this is another picture. This is some patch of sky uh, uh, observed by the Hubble Space Telescope. Each star you see there shining is actually a white dwarf. Okay, and one interesting aside is that if you look at the life history of a white dwarf, ultimately many of them end up with a degenerate carbon core. Okay, and there is some speculation or belief that it's actually even crystalline in structure. Okay, so a carbon crystalline structure, so it's basically a diamond. Okay, so many of these white dwarfs are essentially diamonds in the sky because they, in some sense, have a degenerate carbon core which is crystalline. Okay, but things were a little puzzling, and there were some things which were slightly troubling. And what is this? See, average density of these objects is like m by r cube. It scales like m by r cube. But remember, r goes like m to the power minus 1 by 3. Right? R goes like m to the power minus 1. So average density for these objects goes like m square, mass square, quadratic in mass. Okay. So if you think about it, the more massive these objects get, the more their average density gets. But remember, the average density, if it is larger, the Fermi momenta is also larger. Okay, so this is number density to the power 1 by 3. If you convert it into mass density, rho goes like 1 by 3. So if the mass of these particular objects is getting larger and larger, rho is getting larger, that means the Fermi momenta is getting larger. Okay, but if the Fermi momenta is getting larger, okay, relativistic effect should start becoming important, right? Because as energy becomes larger, the speeds of these constituent particles become larger and larger, and as they approach the speed of light, you should account for the special theory of relativity. Okay, so for example, see earlier, as I'm writing in equation 11 right hand side, for the non-relativistic case, we use energy goes like k square by 2n, k Fermi square by 2n. But for more massive objects, Fermi stars, okay, stars consisting of fermions, which are very compact, more massive, you cannot use kf square by 2n. You have to use the full relativistic expression. E square is equal to k vector square plus n square, where m is the rest mass. Okay, the Fermi momenta still scales like n to the power 1 by 3 because that just came from the uncertainty principle. Okay, so Chandrasekhar had this revelation that for more massive stars, you cannot simply use a non-relativistic treatment, which he had done in 1930. One has to do this slightly more carefully. One has to use a full relativistic expression. But for our purposes, just to simplify some of the expression, we'll actually take the ultra-relativistic limit in the sense that the rest mass m square can be neglected compared to kf square. It's ultra-relativistic. So in the ultra-relativistic limit, if you were to put back factors of C, by the way, I should mention, since I'm a theoretical particle physicist, usually, I work in what are called natural units where h bar equal to C equal to 1. Okay, so sometimes you won't see factors of C. Okay, that's because I'm working in C equal to 1 units. But from dimensional analysis, you can always put back appropriate factors of C. And if you do things more carefully, even order 1 factors of pi, you can put that back in. But I just want to give a flavor for. Okay, so let's work in the ultra-relativistic limit. So Fermi energy is equal to k Fermi. Okay, so now in the relativistic or ultra-relativistic case, the Fermi energy goes like number density to the power 1 by 3. Equation 14. Earlier in the non-relativistic case, remember, the Fermi energy went like number density to the power 2 by 3. But in the ultra-relativistic case, number density goes like 1 by 3. Now, this might not a priori seem like a big thing, 2 by 3, 1 by 3, okay? But, you know, this is actually extremely important, and this is going to lead to some spectacular results. Okay. Now you do the same thing which you did earlier. Now, since it's ultra-relativistic gas, the pressure goes like 1 by 3 times energy density. Again, the energy density is what? The number of particles, sorry, the total energy is what? The number of particles times energy of each particle, but EF is same as KF. So that's why I put KF. Again, it's not that every particle has a Fermi energy. It's like, you know, some factor, but it's proportional to the Fermi energy, some fraction. Okay. So we're just doing an order of magnitude calculation. So the total energy is number of particles times EF, but EF is same as KF. That's a numerator. And since it's a density, you divide by V. Okay. And KF goes like N by V to the power 1 by 3. So you multiply these two, and you see that now the ultra-relativistic limit, okay, the pressure of a fermion gas in the ultra-relativistic limit goes like density to the power 4 by 3, rather than density to the power 5 by 3 for the non-relativistic limit. See, so in the non-relativistic limit, you could actually derive a functional form between R and M. Okay, and it gave you, and in 1930, it gave a very good prediction for what should be the radius of this white dwarf Sirius B, which approximately had 1 solar mass. So now if you take this equation of state, again put it back into the equation of hydrostatic equilibrium, okay, something interesting happens. You don't get the, you know, relation between R and M, okay, because in some sense you've taken the ultra-relativistic limit. You're actually looking at one of the extremities of the case. Instead, what you get, and this can be done even exactly, and I encourage you to work it out with all the, see, as you have seen, everything we have done just uses basic thermodynamics, basic quantum mechanics. You know, there's no, nothing which should not be too unfamiliar to a BSc physics major student. And this is one of the reasons I just wanted to flash this estimate for all of you, okay, and to make a point. So if you do this, if you take this equation of state, again use a hydrostatic equilibrium equation, you get a characteristic mass. You don't get the R versus M, but you get a fixed mass, which is given by this equation 17. It goes like 1 by G Newton to the power 3 by 2 times 1 by M square, where small m is the mass of the formula. Now, G Newton, you can write it in terms of something called the Planck mass. So G Newton is 1 by M Planck square. So if you substitute that in, you will get this characteristic mass, which we today call the Chandrasekhar mass, scales like M Planck cube by M square. You can see dimensionally it is correct. Okay. So what is the story? So as sketched in 18, so in the non-relativistic case, you had a curve. Okay. Now, just in the ultra-relativistic limit, okay, it's in some sense one specific limit of the relativistic case, ultra-relativistic, it tells you that there is a characteristic mass and it says R is equal to 0. Okay. Now, this is nothing peculiar, just saying that there is some instability beyond this characteristic mass M Chandrasekhar. Okay. Now, instead of taking the ultra-relativistic limit, if you just, you know, ultra-relativistic limit, you took EF equal to KF. But instead of doing that, if you took the full relativistic expression, okay, and then solving the differential equation is a little bit more involved, but it can be done. And these days, using MATLAB or Mathematica, one can do it quite easily. If you were to do that, again, you can recreate a curve, a full curve, which is what is being shown by this dashed lines. Okay, so for low masses, the non-relativistic prediction and the relativistic prediction coincide. Not surprisingly, because when mass is small, densities are small, the Fermi momenta involved are small, so the relativistic corrections are not that important. But as the mass increases, okay, the curves deviate, and the relativistic curve actually ends in a characteristic mass, which is called the Chandrasekhar mass. Okay, where on the other hand, the non-relativistic curve predicts something which is, it just continues on. Okay, and observationally, this is not what we see. And by the way, if we take equation 17, have all the factors put in, factors of pi, etc., and if you calculate this, you'll get 1.4 m solar, which all of you know as Chandrasekhar. Okay, so this is just a lightning summary of some aspects of, these conventional astrophysical objects like neutron stars, white dwarfs, etc. By the way, I'll tell you why I use the word conventional. See, in no way are they conventional, okay, but they are incredibly fascinating objects with many properties which we still do not understand. The reason I'm calling them conventional is because I want to tell you about something more speculative, what are called exotic compact objects. Okay, so remember this scaling, mp cube, m Planck cube by m square. Okay? But before we do that, so let me tell you what are some of the things we can understand from these objects, okay? Apart from their intrinsic fascination from the astrophysics side, etc. From the point of view of particle physics, fundamental physics as well, they are incredibly useful and fascinating objects. So for example, one class of neutron stars are called pulsars. You might have heard of this. So pulsars have this radio beam which sweeps across the face of the earth, and they have exquisite timing. So for example, the millisecond pulsars have timing accuracy better than a nanosecond. Okay, every millisecond they sweep through, and the error is of a nanosecond. Okay, to the extent that when they were first discovered by Jocelyn Bell, okay, we did not have atomic clocks which had that much precision. So initially, it was even whimsically thought that there are actually some extraterrestrial civilization. So in fact, she wrote LGM, Little Green Men, okay, during the first discovery. And these pulsars have incredibly strong magnetic fields. Okay, 10 to the power 12 Gauss. Okay, there are even more monstrous neutron stars which have even monstrous magnetic fields, 10 to the power 15 Gauss. Okay, you can ask yourself, what is the largest terrestrial magnetic field we've been able to create in a sustained manner, and it's orders and orders of magnitude smaller than this. Okay, so these neutron stars, okay, for again very fascinating reasons, have incredibly strong magnetic fields. Okay, so you can do, or there could be phenomena near these neutron stars in these incredible magnetic fields which are very unique and which we have so far not seen on Earth. Okay, so quantum electrodynamics is a theory which generalizes Maxwell's equations, for example. It includes the tenets of special relativity and quantum mechanics. Okay, so there are strong field phenomena which you can hope to observe near these neutron stars, which is not possible anywhere on Earth. Okay, these have very strong magnetic fields, they're spinning. Okay, so there are regions called vacuum gaps near these neutron stars where, if you take a strong magnet and rotate, it can generate an electric field. So there are also regions where very strong electric fields are produced. Okay, so there are what are called non-perturbative phenomena where these electric fields can produce hitherto unknown particles which could be existing in nature, And if they are being produced in these vacuum gaps and they're taking away energy from this neutron star, okay, it will kind of demagnetize a neutron star. Okay, so by studying these kind of things, or is it happening? So if you see a neutron star which has lived for, I don't know, a million years or 10,000 years, and it has a sustained magnetic field of 10 to the power 12 Gauss, that means nothing is demagnetizing. Immediately you can say things like, oh, certain kinds of particles and could not be there in the universe. Okay, so these are some of the things which we can leverage neutron stars to study. Another interesting aspect of compact objects like neutron stars is, so many of you might have read that we don't know what about 20 to 25% of the universe is made of. Okay? We have given it a name called dark matter, but we know that it is not any elementary particle which is there in the what we call the standard model of particle physics. So the nature of dark matter is a big mystery. Okay, so we are trying to study, probe dark matter in terrestrial experiments, like at colliders like the Large Hadron Collider, also in underground detectors where we, look, if a dark matter, if it scatters from a nucleus, we look at the recoil of this nucleus and we are trying to detect it or put limits on it, etc. Similarly, you can also use neutron star like a huge detector, okay, to probe dark matter. So, for example, if there's dark matter which is kinetically, passing through a neutron star, hits the neutrons in the neutron star. There is gradual heating of the neutron star. Okay, so if you look at old isolated neutron stars, and if you are able to look at their ambient heating, okay, you can say perhaps something about what could be happening. Okay, or there could be things like you have a white dwarf, and this white dwarf is collecting dark matter, and sometimes these dark matter can annihilate with each other. So this white dwarf could be getting heated up, again some residual heating. Okay, and in some extreme cases, maybe it will even rip apart this white dwarf because of the residual heating. So using things like a neutron star, white dwarf, etc., okay, to probe for dark matter in the universe. Another thing, okay, is all of you know that there are these objects called black holes. And this figure is probably very familiar to all of you by now. It's from the Event Horizon Telescope collaboration. Okay, so there is actually a black hole at the center. Okay, and there is actually something called a photon sphere. Okay, which is outside what is called the event horizon of the black hole. What this photon sphere means is that it is the last orbit where a photon or a light can basically persist without falling into the black hole. Okay, so any orbit inside it, the photon cannot exist in orbit. It will just plunge into the black hole. Okay, but photon sphere is the smallest orbit where basically a light ray can in some sense circulate. Okay, so this photon sphere, when viewed from Earth, okay, because space is curved near the black hole, etc., so it won't be just simply a Euclidean geometry. R theta is the size of the radius of the photon sphere. There'll be some bending. You take that into account. Okay, this goes by the name of black hole shadow. Okay, so this dark region which you see there is related to the black hole shadow. Although, for technical reasons in this figure, it's not technically that, but it's related to things like a black hole shadow. Now you could ask if there are, certain dark matter particles, okay, or some fraction or some component of dark matter, which is extremely tiny charge, electric charge, 10 to the power minus 14 times electron charge. Okay, so for all practical purposes, they interact very feebly. Okay, but if you have a lot of them, okay, so maybe let's say 0.1% of dark matter consists of particles like this. And you know that if you have something like a plasma, charged particle, there's dispersion of light. So similarly, if there is some dark matter environment, and we know from simulations and observation that there are dark matter halos around galaxies at the center, etc. There might be some dispersion of this light if there are milli-charged particles, for example. So they can actually cause some deviation of the black hole shadow. So by exquisitely studying the size and nature of black hole shadows, can we say anything about dark matter particles? Okay, so then again, using gravitational waves, specifically, this end part, what is called the ring down. Okay, so these ring downs, one of their contributions come from what are called quasi-normal modes. They are very similar to the normal modes which you are familiar with. You strike a drum, there is a normal mode, etc. Here they are called quasi-normal because they decay. Okay, it's not like there's a normal mode which persists. They kind of decay. That's why it's called quasi-normal mode. Like, this is like a normal mode in a cup of coffee, for example. You could ask, for example, if there is a dark matter environment near a black hole, how might these ring down signal or quasi-normal modes get changed? Okay, so there are many studies going on today to try to. Okay, so I want to end the talk in the next 10 minutes by telling you another speculation possibility. So, see, we are saying that about 20 to 25% of stuff in the universe is in this form, which we have just named dark matter. We don't know what it is. Okay, see, this 5% of visible matter, okay, consists of a zoo of particles, right? Electron, muon, top quark, up quark, all. So, dark matter sector, it might be a little silly to assume it's a single particle or a single field. We do not know what it is. Okay, so one of the things we might speculate on is, just like we have neutron stars, white dwarfs, which are made up of neutrons, protons, electrons, etc. In this dark sector, could there be extended objects? Okay, extended structures, or even things like stars. Okay, and what might their properties be? So one possibility which people have studied in the last many decades and which have gained more interest in the last few years is what are called boson stars. Okay, so boson stars, as the name suggests, they're made of bosons. This hypothesis, speculation. Maybe the dark matter has some, scalar particles or some Bose particles which might be forming these objects. Now, when I say stars, I want to emphasize, we don't necessarily mean that they shine. Okay, by stars, all that we mean for these objects is that they're gravitationally bound objects, or where gravity plays a role in their structure. And in some sense, stars, even stars we talk about astrophysically, you can think of them as having a negative heat capacity. Okay, you can think about this. Why you can think of them as effectively having a negative heat capacity. So both stars are stars in that sense, that they are gravitationally bound objects. Like gravity plays a important role in their structure, and in some sense they have a negative heat capacity. Okay. Now, even without getting into the details of some quantum field theoretic calculations, etc., so some aspects of boson stars can again just be understood from basic quantum mechanics, and this is what I just want to give you a flavor of. Okay, so assume this object has a size, radius r. So the constituent particles, okay, from again Heisenberg uncertainty principle, okay, should satisfy the momenta mv should go like 1 by 2r. Okay? Maybe I should have just commented on one thing. See, these are Bose stars. So now you no longer have Fermi-Dirac statistics or equivalently Pauli-Regency pressure to give or counteract gravity. Okay, so these objects are actually stabilized completely by just the uncertainty principle. The fact that, when you try to pack something in a smaller space, because of the positions momenta uncertainty principle, the momenta increases or delta P increases. So there is some effective pressure. So both stars, unlike Fermi stars, like neutron star, or their stability or their existence is completely predicated just on the Heisenberg uncertainty principle. Okay, and we want to estimate what their size might be, what is their maximum mass, etc. Just like what we did for the Fermi stars, where we got a characteristic mass. Okay? So to embark on that journey, okay, we use Heisenberg uncertainty principle. MV is momenta. Okay, and you're working again in h bar equal to 1 units. So the momenta, if you're packing these Bose particle in a box one of size 2r, its momenta will scale like 1 by 2r. So velocity will scale like 1 by 2 mr. So the kinetic energy per particle, which is given by half mv square, will scale like 1 by 8 mr square, where m is the mass of this Bose particle. So what is the total kinetic energy inside this Bose star? That will be number of particles times the average kinetic energy, which is 1 by 8 mr square. And that is this equation 21. So total number of particles is just total mass by mass of this Bose. Now, you know from basic Newtonian gravity that you can calculate if you have uniform density sphere, what is its gravitational self-energy. You can calculate that, and that is minus 3 by 5 g m square by r. Okay. So the total energy is given by equation 23. Just putting in equation 21 and 22 together. Now you can ask, okay, what radius for a fixed mass, for example, okay, minimizes the energy. So we are doing an energetic argument or energy minimization argument. Okay, so you do that. You take equation 23. You do dou E by dou R equal to 0, and you will get that the typical radius of a Bose star scales like 1 by m. Remember, the radius of the Fermi star scale like 1 by cube root of m. Okay, here the Bose star, it scales like 1 over. We can actually go further. Okay? So the reason is that, again, equation 25, just like the earlier Fermi star case, said that if the mass becomes larger, the radius shrinks. Right? This is also a prediction in the Fermi star case, except the scaling was different. It went like 1 by cube root of m in the case of the Fermi star. Here it scales like 1 over. But you know, or maybe you have heard that, say, you cannot pack energy or mass, okay, below 2m. Okay, again, this is in units where g Newton is equal to 1, etc. That's why. Okay, so this r equal to 2m is what is called the Schwarzschild radius. Okay, so given a mass m, if you try to pack it into a space smaller than 2m, it will immediately collapse and become a black hole. Okay, so a boson star will have a unique identity only. You keep increasing its mass according to equation 25, the radius keeps shrinking. But beyond a radius, it will not remain a Bose star. It will undergo gravitational collapse and become a black hole. So there is a maximum mass. See, because when mass increases, radius decreases. Okay, but the minimum radius possible for a Bose star is given by 2 times its mass in this unit where g Newton is 1. So that means there is a maximum mass by corollary. Okay, so if you equate equation 25 equal to 2m and ask what that m is, which is m max, okay, you will see that it scales like 1 by g Newton times m. Okay, this is called the Cobb mass, okay, named after Dr. Cobb. He, I think, was among the first people to derive this. Okay, but the interesting thing one of the interesting things I want to point out is, see, we just use basic quantum mechanics, some basic thing about the fact that there's something called a Schwarzschild radius, etc. The maximum mass of a Bose star scales like m Planck square by m. Okay, earlier for the Fermi star, the scaling was like m Planck cube by m square. Okay, so a Fermi star, so you can write m Planck cube by m square as m Planck by m times m Planck square by m. M Planck square by m is the maximum mass of a Bose star. Okay, so Fermi star have an additional big factor sitting in front, m Planck by m. Okay, m Planck is like around 10 to the power 18, 10 to the power 19 GeV. If you take proton, as a mass of the part, fermion there, it's like 1 GeV. So you have a factor of 10 to the power 19 sitting in front for a fermion star. Okay, here is m Planck square by m. So the maximum mass of Bose stars, okay, at least order of magnitude, in this order of magnitude estimate, is actually the maximum mass possible is actually much smaller than what is possible for us. So there could be, and the details, of what kind of boson stars could be there, etc., is very fascinating. I just try to give you a very quick flavor of some of these aspects in this talk with some order of magnitude, semi-quantitative estimates. Okay, so the point is that astrophysical compact objects, whether they are ordinary neutron stars, white dwarfs, or black holes, or more speculative exotic objects like these Bose stars, and there are others like cue balls, gravis star, etc., they can actually give you a window into new physics out there and can enlighten us on the kind of new particles, new fundamental laws which would be operational in our universe. And I thank you for your patience, and I'll be more than happy to take questions.
If you have any questions, kindly do ask.
Please do not hesitate, okay? I mean, I'll be more than, I know, I remember when I was a student, I was always a little hesitant sometimes to ask questions, but please do not, okay? There are no stupid questions, and I'll be more than happy to clarify anything. I went through some things relatively fast.
Guys, you ask questions.
Sorry,
No necessary for.
your voice is a bit distorted. Can you please say that again? Or maybe you can
Okay,
even
sir.
type in the chat.
Can you hear me
Now
now?
it's better. Yes.
Okay, sir. Participants, you can ask your question. You can ask your questions freely. Hello, am I audible, sir?
Yes, you are. You are.
Okay, sir. Participants, you can ask your questions, not necessarily not in the chat box. You can also ask through your mic.
Maybe it's too late and everybody is tired.
And it looks like no one is having any questions, sir.
Sure.
The
So thank you for
nobody
the
had any doubt.
opportunity. Yeah. Oh, there's one question I think in the chat box.
Yes.
Elaborate on the result and please share research directions on the same topic. I'm not sure which result you're specifically referring to, but see, I've just given you order of magnitude estimate, etc. So one good way to learn about some of these things is actually to do a course in astrophysics, basic astrophysics, or like, in a good program like a BSc, MSc program. That would be one suggestion I can give you in terms of sharing research direction. Another thing which I'll highly recommend is there are a series of lectures by Professor G. Srinivasan. It's based on a summer school lecture series he gave at ICTS. I think it's called Quantum Stars or something. And he's a very beautiful lecturer. He's a very great teacher. And he explains some of these order of magnitude things very nicely. So that is one suggestion I have. But yeah, I don't know, Nida, if I answered what you were specifically asking, but this is something I can tell you. Okay, do a proper course if you can on some topics in astrophysics, etc., under a faculty, or do a reading project or a semester project. In terms of books, there are some books, but not all of them are very amenable to self-study, although you can. But this lecture series, for example, is another thing I can suggest. About dark energy, yeah. So I didn't touch upon anything about dark energy. So dark energy is something even more mysterious. So we believe that it's something like 65 to 70% of energy in the universe consists of, we've just given it a name, dark energy. Okay. Observationally, it is very robustly seen that there is no doubt that there is something out there. So basically, it's causing the universe to expand in an accelerated manner. So one possibility is that this dark energy is when you write, so just like Maxwell's equations for electromagnetism, you can write corresponding equations in general relativity, which is a generalization of Newtonian gravity. You can write an equation. It's called the Einstein field equation. Okay. There is one term you can write, okay, which comes from a constant term in the Lagrangian of the Einstein-Hilbert action. This is not important, but either this dark energy is just a manifestation of this constant. It's called the cosmological constant. So it just comes as an additional term in this Einstein field equation. Or it could be something slightly more mysterious. It could be something called quintessence, etc. Okay, so one of the ways you can check whether it's actually just a cosmological constant or it is some phantom field or quintessence is actually by again looking at its equation of motion. Okay, if it's a cosmological constant, it will have an equation of state which looks like pressure is equal to minus rho, where rho is the density. But if it is something else, that constant sitting in front of rho will not be exactly -1, or it will evolve in time. Like it won't always be -1. And there are, many experiments, observations, which are trying to get to the bottom of this. Okay, so that is dark energy. Other questions, comments, speculative questions?
Good evening, sir.
Hi.
Looks like your topic was very clear to all of the participants, and your session about the Fermi energy, black hole, and event horizon telescope was excellent to us, sir.
Yeah, I'm happy. I wanted to give a semi-pedagogical, informal thing, which and since I think Dr. Arulmuri, many of you said many of you are physics majors, I thought I'll also make it slightly semi-quantitative at least. So if you were able to take away at least a few vignettes from here and there, I'll consider this as partly successful. And yeah.
Yes. Thank you, sir. And there are participants in our college attending a live session, sir. They are
Okay,
streaming
okay,
on class, and
okay.
they all were attentive to the class, sir.
I see.
It
Okay.
was very good to know, sir. And your PPT was different from the other PPTs we have seen, sir. It was
Yeah,
good.
I made it, more like a lecture note, more of, like I said, I thought I'll try to, I wasn't sure how successful it will be. If it wasn't, you can even email and tell me it wasn't good. So if you're hesitant to say it here, so I just tried to make it semi-pedagogical. So I thought I'll actually work out some things and just do some order of magnitude estimates just to give you a flavor of this.
Thank you for support,
Yeah,
sir.
yeah.
Congratulations. Thanks.
Okay, thank you very much. And yeah, I'm glad and I'm thankful again to the organizers for the invitation. And I wish you all the best. And I hope to maybe run into some of you at some conference workshop or later at Loyola or here. Okay? Okay. All of you have a good evening and enjoy the sky watching session. Yeah. Bye. I'll log out now.
Thank you, sir. Thank you, sir, for that enlightening talk. Next, we invite Mr. Sugadev, a member of the Astronomy Forum, to deliver the vote of thanks.
Good evening, everyone. It's my great pleasure to have the honor of delivering the vote of thanks on this memorable occasion. On behalf of Loyal Astronomy and Innovative Forum, I would like to extend our heartfelt gratitude to our esteemed chief guest, Dr. Arun, for gracing us with your presence and sharing your valuable insights. I would like to extend my gratitude to Loyola College management for granting us permission and supporting our initiative. Next, I want to express my sincere thanks to our esteemed HOD, Dr. Madhavan, whose generous support was instrumental in making this event a tremendous success. My heartfelt appreciation goes to our forum in charge, Dr. Arun Muli, and our mentor, Dr. Dinesh Raja, for their unwavering guidance and encouragement throughout this journey. I also want to thank all the staffs and non-teaching personnel of the physics department for their assistance and support. I am grateful to our technical team for their tireless efforts in bringing the event to life and ensuring its smooth execution. I would like to acknowledge our forum members for their dedication and hard work in achieving this success. Lastly, I extend my sincere thanks to each and every one of you for your participation and for making this event a memorable one. We hope to see you again at our future events. Thank you all once again. Thank you, sir.
Bye. Have a good evening, everyone.
Everyone, don't just post your name. Also, give us your mail ID.